Hi folks, and welcome back to another review session. We're going to be talking about a lot of these trig identities and how to work with them, especially the double angle identities and the sum and differences and things along those lines. If you have any questions along the way, there's a little chat box over on the right hand side, and feel free to post any questions that you have in there, and I'll be happy to answer them. So without further ado, let's go ahead and get started. So what we'll start with is trying to use these trig formulas and how do they work. So this will be what might seem, it might be hard, might be easy, depending upon your background, but the real trick to this is when we take a look at cosine of pi over 4 minus pi over 6, which one of our trig formulas that we have, or trig identities, can we use? Well, notice this has a cosine of one angle minus another, so essentially this is a cosine of x minus y. Now, with that in mind, the formula that you have there is just that this equals cosine x cosine y, then plus sine x sine y. Now if you want to see these proven, feel free to ask along the way. I can prove them. I might introduce something called Euler's formula, which is a different way to prove things, but you can knock out a ton of these trig identities all at once using this Euler's formula. And that's e to the I theta equals cosine theta plus I sine theta. You can work with that, just a little play on exponents, and you'll be able to solve this stuff a lot quicker. So keeping this in mind, what do we have now? Well, we have cosine of pi over 4. Oops, got a little ahead of myself. Minus pi over 6 equals, well, what happens? Well, our x is now pi over 4, so that's cosine of pi over 4. And then we have cosine of our y value is pi over 6 plus, and then we do the same thing. The x value once again is pi over 4, so we get sine of pi over 4, and then we get sine of pi over 6. So luckily this is in the first quadrant, so everything's positive. We won't have to worry too much about it. But if we're to draw this out, let's go back to our triangles. Pi over 4 is actually a 45-degree angle. If you didn't know that yet, you can do that calculation. So that means you have pi over 4 and you have pi over 4 here. So oftentimes what we know is whatever we put on these two sides, they'll be the same because you have the same angle, and this is a right angle. You can use the Pythagorean theorem, and you'll see that this is square root of 2. This is one that you might want to take the time to remember, just it appears so often. Same thing with the next one, with the pi over 6. So say this is pi over 6. That's a 30-degree angle, and that means this would be pi over 3, which is a 60-degree angle. And so the smaller goes on this side, it goes a 1, a square root of 3, and a 2. If there were a couple of triangles for you to know, these would be the two that I'd really focus on if I were you. They just happen to occur over and over again, and you can actually use these in a general form as soon as you get a terminal point and kind of work from there. So cosine of pi over 4, what is that? Well, you can take this angle and you're supposed to go adjacent over opposite, so, or adjacent over opposite, adjacent over hypotenuse, my apologies there. So this is 1 over square root of 2, or you'll sometimes see that written as root 2 over 2, same difference. Gets the job done either way. And then the cosine of pi over 6, well, pi over 6 is right here, so root 3 is on that side, so you get square root of 3 all over 2, okay, plus sine of pi over 4. Notice it doesn't matter. Sine and cosine, when you're talking about pi over 4, they're going to be the same value. That's 1 over square root of 2. But the sine of pi over 6, that's going to be 1 is the opposite side, and then over 2. So if there's any questions on that piece, please let me know. I'm happy to help with that. So at the end of the day, what do we have? We have square root of 3 plus 1 all over 2 root 2. And some people might say, oh, rationalize the denominator. You can do that as well, and just multiply both top and bottom by square root of 2. So you'll get down below, in that case it would become 4. and then you'd get root 6 plus root 2. Okay, or there's other ways to kind of write that too, but all different formats work. The main thing that I'd focus on is, can you get to this point right here? If you can get there, you're in good shape. Okay, that's what we're kind of looking for. The rest is just a manipulation of those roots. That's it. Okay, I don't see any questions, so we'll keep on moving on. And so we'll see a lot of these formulas pop out in terms of what's going on. So if we have the cosine of A is equal to -5/13 with A in quadrant 2, that's going to be important there, and sine of B equals 4/5 with B in quadrant 1, then determine the following. So first off, before we even go about trying to solve this stuff, in this case you can use the formulas, you have formulas for this. Let's actually try and work out what the heck this thing looks like in terms of what happens. So first off, let me kind of mention, I'll use, this is no longer a unit circle, but it can, well, we can have it be the unit circle for a second. So x equals cosine theta, and the y value equals sine of theta. Okay, so notice in this quadrant, quadrant 2, what happens to your x values? All your x values are negative, but all your y values are positive. So what we have is sine of theta is greater than 0 in this quadrant, but cosine theta is less than 0 in that quadrant. In the first quadrant, everything's positive, so there's nothing to worry about that there. So at the end of the day, we can use a triangle. Just a basic triangle is all we need. And let's say we have an angle A. Now, we'll understand that it's negative just by using this part where we go back to the unit circle. We have cosine theta less than 0. That's the only one we have to watch out for, because A is in that second quadrant. But at the end of the day, we have a right angle, so this is, and we'll put this in this format. So you have cosine A is 5/13 essentially. We just put the negative because of what quadrant it appears in for that triangle. So what does that mean about this side right here? So let's call this B. Well, notice we have 5 squared plus B squared equals 13 squared. So what does that make? That makes B squared, 13 squared I believe is 169, minus 25 is 144. And so if you didn't remember it, this is a 5, 12, 13 triangle. So that B value can be replaced with 12. Okay. Now for the other triangle, let me erase that just to make enough room for what's coming later. We have sine of B, so it's 4 and 5, so we'll have B right here. Now we have sine, so you get 4 over on this side, you get 5 over on this side, and notice if we have A here, A squared plus our 4 squared equals 5 squared, and then what we can see is A must be 3 in that case. Okay, and I'll write that in there. So we have a 3, 4, 5 triangle. So now how do we solve all this stuff? Well, sine of A minus B, you have a formula that talks about this. So that would correspond to sine of A cosine of B, and then it goes minus cosine of A sine of B. Okay, so here's what we do. Sine of A. Sine of A is positive, right, because we're in the second quadrant, and then A, the opposite side is 12, and the hypotenuse is 13. And then for cosine of B, we're looking at the adjacent over hypotenuse, so you get 3, which comes from right here, all over 5. Once again, if there's questions, please let me know. That's what I'm here for. So in the other case, cosine of A, what's cosine of A? Well, we already have that. That's negative 5/13, and the reason it's negative, well, it says it for 1, but it's in the second quadrant. That's what tells us cosine's negative. Keep that in mind for later on down the road. And then sine of b, what's sine of b? Well, that's going to be, we already have that as well. It's 4 over 5. And so we can simplify this a little bit. So you get 65 down below, and notice we'll get 36 plus 20, which is 56 over 65. Okay, questions on that one? Don't see any questions, so we'll keep on moving on. If you have any questions, as I said, once again, just please post those questions. If we have cosine of a plus b, so this one's, people trip this up because the sine kind of does the opposite behavior. Notice we had a minus and a minus. Well, the cosine kind of switches things around. So you have cosine a, cosine b, and then it goes minus sine a, sine b. So the only thing we've done is really replace the x's and y's with a's and b's here. Okay, so we already know what cosine of a is. That's negative 5 over 13. Cosine of b, well, that's going to be 3 over 5. We've talked about that up above. And then sine of a, that's 4 over 5. Or I'm sorry, not 4 over 5. Sine of a, I should be a little bit more careful there. That's 12 over 13. And then sine of b in this case, that's 4 over 5. Got a little ahead of myself there. Okay, so once again our magical number is 65 appearing down below. And we'll have negative 15 minus another 48, so that's 5363. And it should be negative 63, I believe, over 65. Okay, and double check my arithmetic there, but the main part's what I'm looking for you to be able to do. If you can do this, the rest, I mean, you have ways to get the rest of the answer. But for the sake of this, I'm not using a calculator or anything like that for solving these, and that's what I want to try and illustrate here. Okay. So now moving forward on this one, tan A plus B. What's our formula in this case? Well, it gets a little bit more crazy. You get the tangent of A plus the tangent of B, and then all over it goes 1 minus the tangent of A times the tangent of B. So basically all we're doing is finding the formula that applies for right now and solving from there. It'll get a little more interesting when we have a little bit more freedom. You won't have necessarily a plus in there or minus in there. So taking a look at this, what do we have? Tangent of A, what the heck is that? Well, notice it's opposite over adjacent, so it would be 12 over 5. Okay, plus tangent of B. Well, tangent of B, what's going to happen there? Well, in that case, we're going to get opposite is 4, and then a 3 down below. So opposite over adjacent is 4/3. And then it goes 1 minus our tangent of A times tangent of B. Well, tangent of A, once again, we already had is 12/5. And tangent of B was 4/3, so times 4/3. Okay. Now, if you wanted to simplify this, that's fine for me right now, to be honest with you. I'm happy to see that answer. That's good. But just in case, what will we do to try and solve this? We'll multiply both the top and bottom. I'll put it in pink here. So the thing we'll multiply by is 15 over 15. And why 15? Because we'll notice you have a 5 times 3 is 15, and a 5 times 3 to get rid of those denominators. It'll make your life a lot easier. So if we do that, notice the 5 and 15, you'd have an extra factor of 3 up top, so you get 12 times 3 plus 4 times 5 in that case. And then it goes 1 minus, well, if we multiply, oh, I got a little mistake there, not 1 minus, it goes 15 minus, okay, and then when you multiply 15 here, it'll cancel off with the 15 down below, and that leaves us with 48. Okay, so that means we have 36 plus 20 is 56 over, what is that, negative 33, I believe. And that would be your final answer. Okay. Once again, any questions, please let me know. But since I don't see any thus far, we'll keep on moving along. So this is what I kind of mentioned before, is how do we compute the exact value of sine of 19 pi over 12 when we don't have a nice angle sitting inside of there? And this is where we have quite a few different ways to approach this problem. So let me kind of mention, first off, I'm going to go back to the unit circle once again. So we have 0 pi over 2 pi, 3 pi over 2, and then you have 2 pi sitting right in the same spot 0 is. Notice 19 pi over 12, if it was 24 pi over 12, that would be 2 pi. So it's sitting somewhere in between the 0 and 2 pi. Okay, so we're good there. Now let me kind of mark some things that happen here. So if you have, first off, this is pi over 6. We know that angle. Another angle that we know is pi over 4. Okay, and another angle that we know will be pi over 3. Okay, all those are common angles. They're common triangles. We already talked about them, actually, as a matter of fact. And notice I could put them in any quadrant, right? So if I have this, so this angle right here, notice that means that this angle is pi over 3, right? I'm trying to at least make that mimic what's going on there. So if that's pi over 3, notice this angle should be pi minus pi over 3. And so we should have that angle. Well, what angle is that? Well, that should be, so you get 3 pi over 3, so this should be 2 pi over 3. Okay, in a similar manner, we can do an angle like this, where we have pi over 4 sitting right here. Okay, well, pi over 4, so if I go pi, make an angle right there, and then I draw it on out, that would be pi minus pi over 4. So notice that is the same thing as 3 pi over 4. We know that angle as well. Okay, and we can keep on kind of going on down the list, and so we get something like over here, this angle, I should say. Let's take it right smack dab in between there. So that angle right there would be, if we have pi over 6 sitting right here, that would be pi minus pi over 6. So that equals 5 pi over 6. Why is that important? Well, when you think of the sine of 19 pi over 12, we have two formulas that we can kind of work with for the most part. You can do sine of x plus y, which is just sine of x cosine y, plus cosine x sine y. Or you can do sine of x minus y, which is sine of x cosine y, same thing basically with a minus symbol. So we have some freedom to choose how we're going to approach this problem, in which with formula. And so just because you'll see me approach it one way doesn't mean it's the only way by any means. But notice what I want is, I want x plus y to equal 19 pi over 12. Now how do I get 12 as a denominator? Well, when you start to think about it, there's a few different ways. So one, we could kind of work with things like where we have a 6 in one denominator and a 2 in the other. But notice that would reduce back to 6 of some variety essentially. Another sort of thing that we could take a look at. Let's see, what are some other values? We could do 3 and 4 would be another one. That would work out quite well in terms of what's happening there. And we could even do 4 and 6, you know, things along those lines. And so just to kind of give you an idea, let's work with one of the 6's. So notice, to make it easy, I'm going to write x equals 5 pi over 6. So if I have x equal 5 pi over 6, notice that this becomes the same thing as 10 pi over 12. So what would y equal then? Well, so we get 10 pi over 12 plus y equals 19 pi over 12. Now, you might see something fancy happen here. I'll kind of talk about why we made such a selection as this one. It does take a little bit of practice there. So if you subtract 10 pi over 12 from both sides, notice you get y equals 19 pi over 12. And then minus 10 pi over 12. Which is the same thing as 9 pi over 12, but that has a common factor of 3. And so this thing would equal 3 pi all over 4. Notice both of those angles appear up here. And so we're in really good shape because both of them even, and let me kind of circle this here so you can see, 5 pi over 6 is right there, and then the 3 pi over 4 is right there. And so both of those happen to occur in that quadrant. Was this the only choice? By no means. You can start manipulating this. I mean, there's infinitely many solutions for x and y, but finding ones that work are the main thing. Can you, okay, so I see a question that popped up. Can you use the formula to convert radians first, 180 over pi, and then find the degrees? Oh yeah, most definitely. If you prefer degrees, yeah, so you could do 19 pi over 12, and then you need, so this is radians. And if you struggle with that formula at first, I'd recommend this. There's pi radians, because you want the radians to cancel, and then there's 180 degrees in pi radians, right? And so now you can kind of cancel off the pi's, and then you're left with, okay, what's 180 divided by 12, and kind of simplify there and see what your angle is. And so you could try and break apart the angle into angles that you know. That's totally fine, and that's a great approach. And that's why I said there's many different approaches that you're going to get on these. Just because I'm giving you one solution doesn't mean it's the only way. When you see stuff like this, and there's no saying, hey, it's a plus, or hey, it's a minus, you have a lot more freedom. And that's the beauty of these problems. You can take whatever route you want. Okay, so whatever gets you to finding this 19 pi over 12, or whatever this turns out to be. So I don't know off the top of my head what 19 times 180 divided by 12 is, but so let's see here. 19 times 180, what would that equal? About 3,420, I think. And then if we divide that by 12, I think that's about, check me on this, is it 285 degrees? Something like that. But so yeah, you can break apart 285 degrees and kind of work from that perspective. And that's great. If you prefer that, go for it. The reason why you see me work a lot with radians, for those of you that do have to go on, you will have to convert everything to radians when you get into calculus, because these certain properties, when it's called taking a derivative, it won't work for degrees. You'd have to do some adjusting if you have degrees in there, so you want to work with radians just because it makes your calculations simpler, although it seems tough right now. But yeah, definitely go for it. Try and break apart the 285 degrees and the corresponding angles. So that would be 180 minus 30, so that's a 150 degree angle. And what's the other one that we're working with? So we took away a 45, so that'd be 135. So both of those angles we know, and you can break apart it that way. Yeah. Oh, 285. Awesome. Thank you. Appreciate it. I'm glad to see that worked out. So yeah, we have 150 plus a 135 degree angle, and you can work this out exactly the same way as what you're going to see here. So I'll just kind of work with radians just to kind of keep you in that habit. I think that's probably the harder ones that y'all are dealing with, are the radians ones from looking at the homework sets. So I want to make sure we're aware of how to break these things down, but converting it to degrees is perfectly a great approach to these if you struggle with radians especially. So now we need to figure out, okay, what's our triangle again? And so we have a pi over 4, but remember it's technically a 3 pi over 4, so we'll have to deal with some negatives and some positives in a second. So pi over 4, hopefully you're familiar with that triangle. Get 1 square root of 2, and then the other one we'll have a pi over 6, and so that means we have a 1, a square root of 3, and a 2. Okay. Now notice, since we're in quadrant 2, cosine of theta is less than 0 and sine of theta is greater than 0. So keep that in mind. So the one we'll use in this case, I chose addition. Did I have to choose addition? No, we could have chose subtraction and done the same thing, but I find addition's pretty nice. So sine of 19 pi over 12, we just found that that is 5 pi over 6 plus 3 pi over 4. So we're using that top formula. Sine of x. Well, sine of 5 pi over 6, so I did them kind of in the opposite order here. So we'll work with this pi over 6 one. So we want the sine of this. So it'd be 1 over 2. Okay, so we get 1/2. Cosine of y. So you're going to look down on this side. You have, oh, sorry, wrong one. Cosine of y will be right here because our y value is 3 pi over 4. So 1 over square root of 2. But remember, we have cosine theta is less than 0 because we're in quadrant 2. Okay, so you have, this is negative 1 over square root of 2 minus. Okay, so now we have cosine of x, so that would be the square root of 3 over 2, but x, remember we're dealing with cosine now, so we're in quadrant 2 once again, so this has to be a negative value sitting inside of there. Okay, so sine of y, what happens now? So we go back to that 3 pi over 4. Sine is going to be a positive regardless, so we get 1 over square root of 2. And if you want to simplify this, we have the 2 root 2 sitting down below, and so we'll get negative 1 minus and minus makes plus, so you get negative 1 plus the square root of 3, and that might look familiar. We had something pretty similar. So you can write this as, the only difference is you have a negative there. So we could write this as root 6. So first off, we can multiply both top and bottom by 4. So you get, or by 4, by square root of 2 to make 4 down below. And then we'll get negative root 2 plus root 6. And you're done. Okay, so hopefully that was a little more interesting because you had a little bit more leeway in terms of how you could approach the problem. I just want you to see stuff like that because that comes in handy, right? That's what we really want to do, is be able to solve as much as we can without determining many others of those crazy angles. So the same rules apply on this one. You have the tangent of 105 degrees, excuse me there. So if we have tangent of 105, notice we can still go through and mark the angles that we know. And so let's go back to kind of what Charlotte was mentioning. Okay, so what are the angles in terms of degrees? We have 30, then we have 45 degrees, and then we have 60 degrees. And notice right there, just off those two, 45 and 60 degrees, you add those two up, you get 105, right? So I'm going to work with plus 1 again. I don't have to, but if it ain't broke, don't fix it. So we'll work with tangent of x plus y. Everything's in the first quadrant, so we won't have to worry about too much there. So tangent of x plus y, we talked about this. This is tangent x plus tangent of y. And then what's the other one? We get 1 minus tan x tangent of y. Okay, so just for kicks, we'll say x is 45 degrees, and then y would be 60 degrees. And notice then x plus y equals 105 degrees. Okay, just finding some combination. Actually, I will go through the other formula just to kind of illustrate that, hey, you can use two different methods to find the solution. So working with this one, we'll need this triangle. So 45 degrees would be 1 square root of 2. And then we have a 60-degree triangle, which puts the square root of 3 over on this side. Then we have 1 and we have 2 right there. Okay, so that means that this thing equals, so well, first let's plug it in. We have tangent of 45 degrees plus 60 degrees equals, let me write it out, tangent of 45 degrees plus tangent of 60 degrees all over 1 minus tangent of 45 degrees times tangent of 60 degrees. Okay, so tangent of 45 degrees, notice it's opposite over adjacent, so it's 1 over 1, which is just 1. And then tangent of 60 degrees is square root of 3, opposite over adjacent is square root of 3 over 1, which is just square root of 3. So notice you get that, and then you get 1 minus, you get 1 times square root of 3. And so we can write this as just 1 plus square root of 3, and then 1 minus square root of 3. And you're done. That is not the only way, however. Another way, if you wanted to, you could work with tangent of x minus y. Let me write it as x sub 1 this time, minus y sub 1. And that would equal tangent of x sub 1. Oh, excuse that there. Minus tangent of y sub 1. All over, in this case, it's going to be 1 plus tangent of x sub 1, tangent of y sub 1. So any guesses as to what angles we'd use here to try and make it easy on ourselves? What would we want x sub 1 and y sub 1 to be? So notice we want x sub 1 minus y sub 1 equal to 105 degrees. Any ideas on some that we know? So yeah, I actually will repeat the steps for opposite over adjacent. Is it okay if I try doing that for this case? Would that work? And I can go back afterwards to kind of show you. I'll slow it down a little bit. So I'm glad you're asking. That's perfect, Charlotte. So if you look at x1, we can have that be 135 degrees, and then y1 be 30 degrees. Okay? If that's the case, so we get, this is, well, basically I'll try and fit it in here. So if we go 135 degrees minus 30 degrees, notice that changes everything right here and right there. So you get 105 degrees, or 135 degrees, excuse me, and 30 degrees. And then we have another 135 degrees and 30 degrees. So notice, once again, in the first quadrant, sine of theta is greater than 0, cosine theta is greater than 0, and tangent theta is sine of theta over cosine theta, so tangent theta must be greater than 0. In the second quadrant, though, you have sine of theta is greater than 0, you have cosine theta is less than 0, so when you go sine of theta over cosine theta, you go positive over negative, so that means tangent theta, theta is less than 0, so that means it's negative. Okay? So let's talk about what actually happens in this case doing the opposite over adjacent. So let's draw the new triangles. So notice if I go 135 degrees going from here to here, that means that the remaining angle has to be 45 degrees. Okay? So I can reuse this 45 degrees. Just remember that we're going to have negative values. And so that's kind of why I said, oh, can we just do the this triangle? Because you're basically getting the same triangle. Only thing is we're going to put a negative symbol in for that tangent theta when we have 135 degrees. So, but for the 30 degrees, remember it's the 30, 60, 90, but the 30 degrees we'll put the 1 right here. So technically I could have just gone right here and gone 30 degrees and done the same thing. But just for kicks, we'll put 30 degrees and we'll put 1 square root of 3 and 2 right there. So tangent 35. And remember, tangent of theta equals opposite. So the opposite side of the angle divided by the adjacent side of the angle. Okay? So what's the opposite side? Well, let's start with a tangent 135 degrees. So the opposite side, this would be opposite, and this would be adjacent. So when we go tangent of 135 degrees, I'll start it off and I'll put 1 over 1. But I need to remember one other thing. It's in quadrant 2, so I have tangent theta now is less than 0, so I put a negative symbol out in front. So just use the same triangle, but put that negative symbol right there. Now tangent at 30 degrees, okay, let's take a look. So what do we have? We have a 1 is the opposite side, and the adjacent side is square root of 3. So this is 1 over square root of 3. Questions on that piece? So now, on the bottom part, we get 1 plus, remember tangent of 135 degrees, we already had it from up above, it's in that first position right there. So we get negative 1 over 1, and then the second one is 1 over root 3. Okay. Does that make sense, and does that help with seeing how the fractions work with opposite over adjacent? If not, let me know and I'll try and go back and go through the first one as well. So now you might say, oh, wait a second, Josh, this is different than the first answer. And I'll say it looks that way, but I'll kind of prove that this is the same exact thing. So moving forward from here, notice we have negative 1 minus 1 over root 3. So another thing that we can do, and let me put it in red again. We can multiply the top and bottom by root 3 over root 3. Just to try and get it to match that top one. So when we do that, we get negative root 3, and then the root 3's would cancel in the second case, and we'll get minus 1. And in the bottom, we get 1 times root 3, which is root 3, and then we'll have minus, and then the root 3's will cancel in that second one, and we'll just be left with minus 1. And you might say, that's still different. Right? And that's fine, thinking that's different. But what actually happens is you can factor out a negative 1 in the top. So you get negative, and then you could write this is root 3 plus 1 over root 3 minus 1. And then you can multiply both the top and bottom by a negative symbol, because that would still be 1. You're doing the same thing. So multiply by negative 1 over negative 1, and that changes your top to root 3 plus 1, and then it would become negative root 3, negative root 3. Let me rewrite that so it looks a little better. So this would become negative root 3 plus 1, which you can reorganize to make it put the 1's in front. So you get 1 plus root 3, 1 minus root 3. So getting the same answer, a few more steps, but you can see that it doesn't matter which route you take, you can still find answers. And these angles, you might find other angles that could work too. Okay, so keep that in mind as well. Hopefully that makes sense on that piece. If not, let me know, and hopefully just let me know if that didn't work for the opposite over adjacent explanation as well, where we're kind of looking at on the triangle. I'll be happy to go back through that again. Okay, so now a lot of this trig identity stuff that you see is basically simplifying, And so I'm not going to try and say, okay, here's the final answer that we get to. I'm just going to try and simplify this junk and see what the heck this thing looks like. So you see a cosine theta minus alpha on the inside, and then you have sine of theta, sine of alpha. What the heck is going on here, right? And so what we want to do is try and simplify, get rid of the minus alpha, theta minus alpha if possible. Okay, that's usually your best bet. And so if you recall, well, let me write down the first one, cosine theta minus alpha, sine of theta, sine of alpha. And so notice you can't really break down sine of theta too much more. You can't break down sine of alpha. We will have cases where we'll be able to break down. If I had sine of theta, cosine theta, that'd be something different. But in this case, the main thing that we have a formula for thus far is theta minus alpha, cosine of theta minus alpha. So using the x minus y, replacing that with theta minus alpha, you get, the top becomes this formula. You get cosine theta, cosine alpha, and then it goes minus sine of theta. Oh wait, no, not for this one. I'm sorry, the plus, because we got the minus on the inside. So it goes sine of theta, sine of alpha. Sine of alpha. And all of this is over sine of theta, sine of alpha. And the reason I want you to see this one is because a lot of people struggle with these fractions. How do you break this thing up? Well, break it up into two different fractions first, because you have that plus sign in the numerator. If it's a plus sign in the denominator, it's a lot harder to work with. But since there's a plus sign in the numerator, you can write this as cosine theta, cosine alpha, all over sine of theta, sine of alpha, plus sine of theta, sine of alpha, and then sine of theta, sine of alpha. And you might say, well, Josh, this looks so much more complicated at first, and I might agree with you for a second. But then what you can do, if you notice, what happens on the right hand side is this crosses off with this, and then your sine of alphas will cross off. So that means this whole thing just becomes 1. Okay? So that whole piece is 1. And then I'm going to rewrite the other part. You can rewrite the other part as cosine theta over sine theta times cosine alpha over sine of alpha. And then we have plus that 1. Do any of you know what cosine theta over sine theta is? What's the other trig function that is? I'm interested to hear what you think it might be. Very good. So Josh, you can shoot me an email. You'll get extra credit for that. It is cotangent. So the easier way to write this is just cotangent of theta. And you have cotangent of theta, you have cotangent of alpha plus 1. And I'm not saying this is the only format you can write it in whatsoever, but I don't know, if you look at the first one and compare that to that last piece, I would say that last piece looks a lot simpler. And that's kind of the whole idea, is all we did is just use identities, and the rest, I know it sounds kind of funky, but we were using algebra. I mean, look, we're canceling things out, right? And that's the whole idea. We got 1. Okay, so now the next part was a little bit of trig. You had to do cosine over sine. What does that become? So cosine theta over sine theta. Well, that's cotangent theta. And then same thing for the alphas. But at the end of the day, a majority of it's just manipulation of the symbols. Okay? And that's a lot of our trig identities. And don't worry, I'll work a few more later on once we toss in a couple more. But I just wanted you to get a flavor of what is a trig identity. What are you actually doing? You're just pushing around symbols and using the formulas that you already know. Okay, so our next bit, just to make sure that we have the tangent stuff hit home, we have tangent alpha equals 2 and tangent of beta equals 5. Then determine the following: tangent alpha minus beta and tangent alpha plus beta. The beauty on this, we don't even have to draw a triangle, because tangent alpha minus beta, if you just use the formula, the tangent of x minus y, and replace that with alpha and beta, you get tangent of alpha minus tangent of beta all over 1 plus tangent of alpha, tangent of beta. And so alpha is 2, beta is 5, and this is 1 plus 2 times 5. So it should be negative 3 over 11, and you're done. So if you know the formula, stuff like this does get a lot better. Same thing on the second one, you get tangent of alpha plus tangent of beta. All over 1 minus tangent alpha, tangent beta. And notice in that case we get 2 plus 5 all over 1 minus 2 times 5. Okay, so this becomes 7 over, well, that'd be negative 9 down below, and you're done. That's all there is to this one. So at the end of the day, when you see stuff like that and it's using the same symbols, so the tangents are nice because these tangents just give you other tangents involved over on that the summation formula involved with this one. Okay. So now, moving forward, we're going to get into some double angle and half angle and things like that. You can do all those. So sine of 2 theta, what the heck does that equal? Well, that's 2 sine of theta times cosine theta. And so if we have sine of theta equals square root of 5 over 5, we're good there. So you get 2 times the square root of 5 over 5. But now the hard part is we'll have to go back to the unit circle, and we'll also use a triangle. Unit circle, and we're in quadrant 2 once again. So notice that means sine of theta, the y values are greater than 0. The cosine of theta, though, the x values are less than 0 there. Okay, so when we look at our triangle, if we have theta right here, what's actually happened? Well, you have square root of 5 on the opposite side, and you have 5 on the other side. So if this is a, you have a squared plus square root of 5 squared equals 5 squared. So notice a squared equals 20, and that means a equals the square root of 20, which you could pull out a 4 from that, so you could rewrite this as 2 times the square root of 5. So this becomes 2 times the square root of 5. Okay, but so now the cosine is adjacent over opposite, so this 2 square root of 5 all over 5, but cosine theta is less than 0, so that's negative in this case. And so now the beauty of this is when you multiply all that together, what do we have? We have square root of 5 times square root of 5 makes 5, and 2 times 2 makes 4, so you have 4 times 5 times 25, or divided by 25. And so that'll cross off there and leave you with 5 down below. So our final answer is 4, oops, I forgot the negative symbol, negative 4 over 5. Questions on that one? Seeing how that works out. And we already have the cosine and sine, and so that's going to be useful because cosine of 2 theta, the formula for that one is cosine squared x minus sine squared x. Okay. And so cosine, another way to write this, what people kind of freak out about at first, it's not too bad. This is just cosine of x squared. Sorry, I'm writing x. I meant to write thetas. Just a habit, I guess. So this is just cosine of theta squared. and then minus sine of theta squared. Well, we know what cosine of theta is. We just did that. It's going to be negative 2 root 5 over 5, the quantity squared, minus sine of theta is going to be just root 5 over 5, and that quantity is going to be squared. Okay, so this equals, this is going to be, your negative will go away in the first one, so this becomes 4 times 5 all over 25 minus, this will be 5 over 25. Okay, and so your 5's will cancel, by the way, and leave you with 5 down below. And so this whole thing should equal 3/5. Okay, so which formula is this? And I see you wrote never mind, and I used one of the 3 formulas. Yeah, there's actually many others I could use. I could use, in this case, the sine of the 2 theta. I could have broken this up, sine of theta plus theta, and then I could get sine of theta cosine theta plus cosine theta sine of theta. In fact, we're going to talk about this a little later. This is how we go about proving sine of 2 theta equals 2 sine theta cosine theta. So yeah, in terms of which one, I'm just picking one. If you can find anything that has cosine of 2 theta or anything that has sine of 2 theta involved, you're in good shape. It doesn't matter which formula you use, but you want to find something that has that sine of 2 theta or something that has that cosine of 2 theta, and hopefully reduces your value of your angle on the inside. So notice how we drop down to a theta in these cases. So there's nothing to worry about in terms of, we don't have to worry about changing this angle where we have our information. So see how that's theta right there? That's important, okay? So that's what we're basically looking for, is trying to reduce that power to where it's always just the angle itself, or some angles we know. In this case, you're given an arbitrary theta, so you can't work with it. But in general, you might have, say, something like, maybe 120 degrees or something like that, which we wouldn't know that one actually off the top of our heads. But just for an example, I could break down 120 degrees, I could break it down into two things that involve 60-degree angles and solve for it that way, right? So that's kind of what we're getting at, is how can we break these things down and make them work nicely for us. So not saying it's an end all be all. We could be here all night actually with all the different trig identities that exist out there. These are just some of the big ones that you're going to need to use over and over again. And hopefully that answers your question, Charlotte. If not, let me know. Yeah, so in terms of what's going on. Now, more simplifying the expressions. If we have simplified this expression, cosine 2 theta over sine squared theta, so how the heck does this work? Well, it's the same thing as most trig identities, so you might want to work with a sine squared theta, but notice it'll probably put a summation down in the denominator, so that makes it harder for us to work with sometimes. Not always, but a lot of the times it does. So we probably want to work with the cosine of 2 theta, and we have an identity for that one that we just talked about, and that's cosine squared theta minus sine squared theta. Whoops, what the heck happened there? Sine squared theta and all this is over sine squared theta. Okay. Now, you can break this up once again. This is cosine squared theta over sine squared theta minus sine squared theta over sine squared theta. You might recognize this is very similar to something we did before, just happened to work out that way. When you have cosine squared theta over sine squared theta, you can rewrite that as cosine theta over sine theta, the quantity squared, minus sine squared theta over sine squared theta, that's just going to be 1 because the tops and bottoms cancel. Cosine theta over sine theta, what does that equal? Well, that's just cotangent theta. We talked about that before, and we're squaring it, so we'll write that as cotangent squared theta, and then minus 1. And actually, this gives rise, there's other identities you can use to try and manipulate this even more so. So you could even put this in terms of cosecant squared and things like that. But just keep in mind, this is one of the many different simplified forms. So we've just simplified this, so we have no more fraction. Everything looks nice, hunky-dory. So yours will be more specific in terms of where you're wanting to go with it. Usually you'll have a list of, oh, are these equal? And you can always reduce it down and see once you kind of break with a fraction. And so one that might be a little bit more interesting is this cosine to the fourth minus sine to the fourth, or cosine to the fourth of theta minus sine to the fourth of theta. How do we break this thing apart? Well, this looks kind of nasty at first. And what you might recognize, or you might not, just depends, is that this is a difference of squares. And what do I mean by that? Well, there's a nice formula. If you have a squared minus b squared, that equals a plus b, a minus b. Now you might say, oh, but this is to the fourth. Well, notice, what does that mean? Well, if I have a to the fourth minus b to the fourth, notice as the square is squared, so basically I can write this as a squared plus b squared, and then I have a squared minus b squared. Now you might say, okay, well, what's the big deal? Well, if I let a equal cosine theta, and if I let b equal sine of theta, notice all of a sudden we have a factorization for this formula. So we can write this as cosine squared theta plus sine squared theta, and then we have cosine squared theta minus sine squared theta. Okay, so with this in mind, I'm going to ask you two questions, and so each person you can have one that's involved here. I want to know a nice simple identity for cosine squared theta plus sine squared theta. Tell me what that one is. And then somebody else, you can write me what a nice identity is for cosine squared theta minus sine squared theta. I'll give you a couple of minutes. Try and type that in there and let me know what it is, and we'll go from there. And you can label them number 1 and number 2. So number 1 will be the cosine squared theta plus sine squared theta. Which one is that? And the second one would be cosine squared. So number 2 would be cosine squared theta minus sine squared theta. What identity do we have for that one? And these are pretty common trig identities. That's why I kind of ask along the way. So it's pretty close on that. I liked how the sine, that seems to be pretty good. Well, let's start checking out some things. Rather than doing a general theta, if I take sine squared of 45 degrees plus cosine squared of 45 degrees. Okay, let's see what happens. Well, notice that's 1 over root 2, and we're squaring it, right? So I see the next one. Cosine of 2x is right on the money. So the second one happens to be cosine of 2x. That's exactly right. So good job. And Charlotte, send me an email. I'll give you extra credit for that one. So in the other one, though, let's talk about this, because this is a common one that we might have forgotten about. Sine squared 45 degrees plus cosine squared 45 degrees. So notice that's 1 over root 2 is the sine of 45 and cosine of 45. So we got to square that, and then we're going to take 1 over root 2 and square that. I want you to see what that equals. Then we'll try sine squared of 30 degrees plus cosine squared of 30 degrees. Alright, let's see if we can find this number. Well, sine squared of 30, so sine would be 1 over 2, and we want to square that. And the other one is square root of 3 over 2, and we want to square that. What do each of those equal? So notice we have 1/2 plus 1/2. And in that first case, we get 1. What about our second case? Well, notice you get 1/4 plus 3/4. That's also 1. Does that happen all the time? Well, yes, it does. In fact, the cosine squared plus sine squared of theta, or cosine squared theta plus sine squared theta, or sine squared theta plus cosine squared theta, whichever way you want to write it, it's always going to equal 1. That's a really nice result that if you haven't seen before, you're going to see soon enough. And so this whole thing boils down to just cosine of 2x, and you're done. Okay. And if you're wondering on why that works out for the sine squared plus cosine squared, let's talk about it real quick. Let's say we have a triangle, a right triangle in general, and we have some theta, and we have A, B, and then we have C. We know the one property that we have is a squared plus b squared equals c squared, right? So when we take sine squared theta plus cosine squared theta, notice the sine of theta would be a over b, or a over b, I'm sorry, a over c, the quantity squared. And the cosine squared theta is b over c, the quantity squared. And so this would be a squared plus b squared all over c squared, right? So now if you take a look at this one, what's a squared plus b squared? Well, a squared plus b squared, notice we have right here that it equals c squared. So this is c squared over c squared, and so that equals 1. And so hopefully that makes sense in terms of why this property holds. I mean, you can hopefully see no matter what angle we put in there, I don't care what theta is, if we have some right triangle, we're always going to get 1 as a solution there. Okay. So I'm glad to see that helped a little bit. Awesome. And so hopefully that clears up that quiz and whatnot. So on this one, we'll kind of use that same idea. If we have this 1 minus sine squared alpha all over secant of alpha, the big one that I would recommend knowing, and we just kind of mentioned it, is the fact that you have cosine squared theta plus sine squared theta, and I know these are alphas, we can deal with that in a second, equals 1. So that means if you put that sine squared theta over to the other side, notice you have cosine squared theta equals 1 minus sine squared theta, right? So keeping that in mind, what happens? Well, the numerator just becomes cosine squared, instead of theta, it's alpha. In the denominator, what the heck is secant? Well, the secant is 1 over cosine, right? So notice this thing equals the same thing as cosine squared alpha times, remember when we divide by a fraction, it's the same thing as multiplying by its reciprocal. So this is cosine alpha over 1, which is just cosine alpha, by the way. So this whole thing that looks real nasty up front is just cosine cubed of alpha. And that's what happens a lot of times. You'll see a lot of these tricks in terms of, oh, this looks real nasty, it's horrible, and it'll just simplify to something like sine cubed, cosine cubed, or whatever the case may be. In this case, it was cosine cubed. Okay. The real trick is to be able to understand that sine squared theta plus cosine squared theta equals 1. That's a big one. And then know your regular trig functions. Know what cotangent is, cotangent of theta in terms of sine and cosine. Know what cosecant is in terms of sine and cosine. Know what tangent is in terms of sine and cosine. Know what what one am I forgetting? Secant is in terms of sines and cosines. If you can do those, you're going to be in pretty good shape when it comes down to it. So, okay, so let's work with this one. You have sine of 15 degrees and cosine of 15 degrees. And the big thing that has sine and cosine, and we don't know what 15 degrees is, but notice that you have something that has both of those. Sine of 2 theta equals 2 sine of theta cosine theta. Right. So if we wanted sine of theta and cosine theta, because that's essentially what we have here, notice that would equal 1/2 sine of 2 theta. So this would be the same thing as 1/2 sine of 2 times 15 degrees, which is just 1/2 sine of 30 degrees, which is a lot more convenient for us to work with because we know that angle, right? And you can see how often we're going back to these triangles. So this is a 1 square root of 3 and 2 triangle. So this is going to be 1/2 times 1/2, right? Because sine of 30 degrees. So this is 1/4, and you're done. Right? All we do is find that right trig identity to work with, and not saying this is the only one, but it's probably our most convenient in terms of what happened. Okay, next formula. Let's see what happens. All right, derive the identity sine of 2 theta equals 2 sine theta cosine theta. So there's a couple different ways, and I'm actually going to show you both of them. One will be the more straightforward way. So all I'm going to do is I'm going to use sine of x plus y equals sine of x cosine of y, and then plus cosine of x sine of y. So keeping that in mind, you can rewrite this as sine of, so well, first off we'll write 2 theta. So one way to write sine of 2 theta, you can rewrite this as sine of theta plus theta. And this becomes sine of theta cosine of theta plus cosine of theta sine of theta. Well, notice both of those are the same thing. They're just written multiplication commutes, so you're good there. So the same thing if you have one of a certain thing, one thing, and then another thing where they're both the same thing, that means you have 2 of those things. So this is 2 sine of theta cosine theta, and notice you have one side in a whole bunch of equalities, so that means these 2 sides are equal. And that's it. You're done. Right? I'm going to show you another method just for kicks, because it can prove all the trig identities, even this one right here, and it's based upon Euler's formula. And what does Euler's formula state? It says, hey, if you want to work with e to the I theta, first off, this is equal to cosine theta plus I sine of theta, where I is the imaginary number, so I equals the square root of -1. Right? You may say, whoa, wait 1 second here. Why do we want to work with this? And I'll kind of show you why. So one of the angles we want to work with is 2 theta, right? So how do we get that identity? Not only will we get the 2 theta, we'll get another one for free here. So rather than plugging in theta right away, I'll put e to the I 2 theta, and notice we get cosine of 2 theta plus I sine of 2 theta, right? And you might say, whoopity-doo, Josh, right? You haven't done anything yet. But the beauty on Euler's formula is we can write these things in different ways. So you can rewrite this as e to the I theta, the quantity squared, okay, just by properties exponents. So if you're comfortable with those exponential functions, you can really start to work with some stuff here. And so you get cosine theta plus I sine theta, the quantity squared. Okay, now what the heck does this do? Well, if I square this, and just recall, I'll write it off on the side, a plus b, the quantity squared, equals a squared plus 2ab plus b squared. So that means this is cosine squared theta plus, now 2a, so our a is cosine, so 2 cosine theta. Our b is I sine of theta. And then plus b squared. So that would be I squared sine squared theta. You might say, well, Josh, once again, this doesn't do much for us, but I might change how this thing works. I squared, you notice if I square that, I get -1. And so I get -1 times sine squared theta. So I'm going to rewrite this. Anything that has an I together, I'm going to group together. Anything that doesn't, I'll group together. So we'll move this over into that position, right next to that. So this will be cosine squared theta minus sine squared theta. I'll group that together. Plus I times 2, and then I'll rearrange this. So I'll just swap where you see the sine of theta and cosine theta. So 2 sine of theta cosine theta. So now who cares, right? Well, actually we just did something for free. You have an I here and you have an I there. So that means that since that's the only imaginary part, that means that this must equal this piece. So from that you get the identity. Sine of 2 theta equals 2 sine theta cosine theta. But that's not all. So notice the other part, and I'll box it in here. That's the real part of this, not the imaginary, so it's the real because it doesn't have an I times it. So we get another identity. And for free we get the cosine of 2 theta equals cosine of squared theta minus sine squared theta. And in fact, what you're seeing happen here, this Euler's formula, as I mentioned, if you started to replace theta, so if you let theta equal x plus y, you get those trig identities for sine of x plus y and cosine of x plus y, all for free, right? So those are other ways. If you want to use Euler's formula, you can pretty much get all the trig identities that we're working with here. Okay, so I just wanted you to see that this is actually, it comes into play for those of you that are engineering majors and things along those lines. Very useful formula, that Euler's formula, and you'll see it all the way up in Diffie Q. It really becomes important. So last but not least, we're going to do some trig equations and kind of solve these things. What the heck does this look like, right? And what a lot of this boils down to is trying to determine what the heck these values are in terms of how the multiple repeats, I should say. So when we take a look at this, let's see. And the first thing, if you treated this as y, and I said solve for y, could you do it? And my claim would be, yeah, it would be pretty easy, right? So you go 3y minus 1/4 equals 0, and then you go 3y equals 1/4, divide both sides by 3, and you get y equals 1/12, right? Now the only thing is we've replaced cosine of x with y. So it's essentially, here's what we get. We get cosine of x equals 1/12. So the easy solution, what people often see, is that, hey, this becomes x equals the arc cosine of 1/12, and we're done. The problem is what are the values that we get? So when you think about this, the range is 0 to pi, right? So what's happening here? So let's say we're on a unit circle and we get this value, right? So this is the angle, let's call it theta, where you have and actually that's a bad example. I shouldn't have drawn it right there. To be a little more accurate, probably want something like this. We'll call this theta. That'll be a little bit better. Because our x value equals the cosine of theta. So what's happening here? And we're going to say that this is the x value corresponding to that point right there is 1/12. So all the way down, this is, I should put it down here, is 1/12, right? Okay, so keeping that in mind, we said that the only range for this sort of arc cosine of 1/12, whatever number that might be, and you can plug it into a calculator, get an answer, but whatever number that might be, it only ranges from 0 to pi. Well, notice I can have an equal angle on this side that also gives us 1/12. It's just not included in the arc cosine. So what that means is we can have arc cosine of 1/12, but the range is from 0 to pi. So this is not going to be the only solution. And so we're going to have to take 0 minus, right, arc cosine of 1/12. Because that would be on that negative side of things, okay? So you could just call that negative arc cosine of 1/12. This won't always work for all the others in terms of if you're dealing with arc sine and things along those lines. It gets a little bit trickier too. But now, notice we've gone from 0 to pi. Well, what happens if I make a full circle from here? Well, if I make another full circle, I'm back to the original angle. So those are all possible solutions, however many times we make a circle. So if I do one full circle, two full circles, well, what's a full circle? So it'd be plus 2 pi k, where k is an integer. Same thing happens down below. This goes 0 minus arc cosine of that 1/12, and then plus 2 pi k, where k is an integer. So if it asks for an exact value, we've given an exact value essentially, because we don't have the arc cosine of 1/12 off the top of our heads. But you can punch it into a calculator if you're needing some decimal approximation. Now if it restricts the domain, like it says, hey, I want to have it between 0 and 6 pi, how many times does it occur? Well, you just plug in, keep on plugging in for k, start with the integer 1, 2, 3, 4, and see how many times it fits inside of there. Right? And then once it goes outside of that 6 pi or whatever the magical value is, you've figured out, okay, this is my full solution. Okay, in a similar manner, let's try and see if we can do this next one. So we have 3 root 3 secant of x plus 7 equals 1. You can do the y substitution, y equals secant of x, and work from there. If you want me to do that, I'm happy to. But just so you can see it a slightly different way, 3 square root of 3 secant of x, I'll first subtract 7 from both sides, you get negative 6. And so then what do we get? So from there we'll get 3 square root of 3 we need to divide by, so you get secant of x equals negative 6 over 3 root 3, which luckily that can simplify to secant of x equals negative 2 over root 3. And you might not like secant of x, so we can fix that too. We can write secant of x is 1 over cosine of x equals negative 2 over root 3. And so that means cosine of x, once again our lucky cosine here, is negative root 3 over 2. Now this one's a little bit more familiar to us, hopefully, and we should be able to get the angle. So You can do the arc cosine, but at the end of the day we have some triangle over here, who knows where it would be, because you have negative for the cosine, and it has to be between 0 and pi. We know it's going to be in that sort of quadrant to start. So notice we make our triangle, and let's think about this. We have a root 3 on the adjacent side, we have a 2, and that means a 1 must appear on the opposite side. So what angle is this? Well, that's the smaller angle on the opposite, so that means this is a 30 degree or a pi over 6 is what's happening there. And so if that's the case, we get x equals, remember, in order to get this angle here, we have pi over 6. So that means that this angle from here to here must be pi minus pi over 6, which is equal to 5 pi over 6 for that angle right there. So one of the possibilities is, and before I'll write this as a possible solution. So we get 5 pi over 6, and then remember we can go around a full circle, so plus 2 pi k where k is an integer. But this is not all. Remember, we're outside of our domain, or outside of the range in certain cases. So I can do pi over 6 also in this range, right? Because that would give us the same x value that does this. So that means if I add pi over 6, so if I take this angle all the way with that sound effect too, so this would be pi plus pi over 6. And so that would be 7 pi over 6 plus 2 pi k where k is an integer. And once again, we want to try and make sure if you have certain restrictions on what sort of range they want to see. Is it between negative 5 pi and 3 pi? And then you just plug in the values for the integers and make sure until they fall outside of that range. So hopefully that makes sense on that part. So a couple more real quick. Let's see if we can work these out. So you see a cosine squared minus 2 equals 5. You can write a y, then you'd have 7y squared minus 2 equals 5 as well. That works. Or you can just solve it as you would a polynomial. Subtract 5 from both sides, you get minus 7 equals 0. Notice 7 is in common with both. So you get cosine squared of x minus 1 equals 0. So essentially this boils down to y squared minus 1 equals 0, right? Okay, so how do we factor that? Well, that's y plus 1, y minus 1 equals 0. Okay, so that means we have 7. This is cosine of x plus 1 equals 0, and cosine of x minus 1 equals 0, that we're going to set each factor equal to 0. So erasing that piece. If you prefer the substitutions, please let me know. I'm happy to go through those. So if we go cosine of x plus 1 equals 0, notice you have cosine of x equals negative 1. And there's only one place at first where that actually occurs. And so where would that be? Well, cosine of x equals negative 1 when x equals pi, but also plus 2 pi k where k is an integer. Okay, and then when we go cosine of x minus 1 equals 0, you get cosine of x equals 1. And the only place that this happens is when x equals 0. Because what we're doing in both cases, you have that unit circle. One occurs when the angle is 0 there. The other one occurs, so this is negative 1, that's positive 1. So at this angle pi here. So 0, and then this one's plus 2 pi k, where k is an integer. Okay. So moving forward, we can do a couple more. You have 2, and this becomes sine of x, or sine squared of x, but minus sine of x. Most times people try and divide by sine, you'll lose a solution that way. Factor it like a quadratic, same song and dance. So this thing becomes, well, let's factor out the sine of x from both parts. And notice you'll get 2 sine of x minus 1 equals 0. So in this case, you get some interesting stuff that happens here. You get sine of x equals 0. So when does that occur? Well, if we look, sine of x equals 0 at this angle and this angle. So notice that's just pi over 2, and then 3 pi over 2 you could do plus 2 pi k. Or an easier way for us to write that is x equals pi over 2 plus pi k, where k is an integer. Or you could do, as I said, pi over 2 plus 2 pi k, and then 3 pi over 2 plus 2 pi k. It's the same song and dance. You'll get the same solutions that way. In our other scenario, 2 sine of x minus 1 equals 0. That means sine of x equals 1/2 when you solve that. So where would that occur? Well, notice we're looking for a triangle that has a 1. We have x sitting right here. And we have a 1, and then we have a 2, and then we have a square root of 3. Well, what is that? Well, we already talked about it as 30 degree, or x equals pi over 6. So you have pi over 6. So x equals pi over 6 plus 2 pi k. Where k is an integer. Or another place where that can happen, the other y value where this can occur is right over here. And so notice you'd have another pi over 6 angle here, but that means that this must be pi minus pi over 6, which is also 5 pi over 6. So 5 pi over 6 plus 2 pi k, where k is an integer. So a lot of this falls back to the unit circle in terms of where are we getting our solutions. Okay, so let's take a look at a couple last pieces here. If we go 2 cosine squared x minus 7 cosine x minus 4 equals 0. Once again, we have 2y squared essentially minus 7y minus 4 equals 0, where y equals cosine x. So you can factor that thing. Notice you can factor it 2y plus 1 and then a y minus 4. So this means we have 2 cosine x plus 1 and a cosine x minus 4 equals 0. So in the first case, 2 cosine x plus 1 equals 0. Notice you get cosine of x equals negative 1/2, which is all hunky-dory. So where's that going to occur? Well, let's first talk about what sort of angle we have going on here. So you have 1 here and 2 there. That means there's square root of 3 here. So that means this has to be pi over 3 this time. So we have, it has to be in the second quadrant. This is pi over 3. So that means we get that this angle from here to here must be pi minus pi over 3, which is 2 pi over 3. So x equals 2 pi over 3 plus 2 pi over k, or 2 pi k, where k is an integer. And the other value, if you go, oh, that was supposed to be where these line up, right? Sorry about that. But so if I go another pi over 3 in this vicinity, I get the other value of pi plus pi over 3, which is 4 pi over 3 plus 2 pi k, where k is an integer. Okay, so now if you're looking at this piece, what's remaining? Set that equal to 0. Notice you get cosine of x equals 4. Cosine of x, the maximum is 1 and the minimum is -1, so this is impossible. So you can't get that factor equal to 0, so your whole solution is just right there based on those two. Okay, so for our last scenario, notice you can factor out a 4 and a tangent of x, and that means we get a tangent x plus 1 equals 0. Woo. So now the fun begins. So in this case we can do this angle as well. You can set tangent x equal to 0. Where the heck does that thing equal 0? Well, notice this is sine of x over cosine of x equals 0, right? So that implies that sine of x equals 0. Well, where does the sine of x equal 0? Sine of x equals 0, if you look back at your unit circle, oh, nope, wrong spot, sorry about that. I was doing the cosine. Sine of x equals 0 is 0 and pi. So any multiple of pi, essentially. So this is x equals 0 plus pi times k, where k is an integer. And what's the remaining piece here? Well, let's take a look at tangent of x plus 1 equals 0. That means you get tangent of x equals -1. So where are we looking for? Well, if tangent of x equals -1, first off, we have 1 on this side, 1 on this side. That means square root of 2. That means this has to be a pi over 4 for our angle. But keeping that in mind, we'll go back to our circle real quick. In order for it to be negative, we need it in one of two quadrants. And so the 1 value would be right here, having pi over 4, which means that this angle has to be pi minus pi over 4, or you can do a subtraction of pi over 4 there, and notice we have something nice happen, right? It just seems like we're adding pi k every time to whatever solution we get here. So pi minus pi over 4, we get x equals 3 pi over 4. Plus, notice if you added just another pi, you get 7 pi over 4, which would be just enough to match that value. This is going to be this angle. Oops, sorry, you don't need that piece. Okay. This angle's 7 pi over 4, which is just adding pi to this. So plus pi k, where k is an integer. And that is the whole idea. Over and over and over again, we're going to be using this sort of stuff. Okay? So hopefully that made sense, gave you a few answers to your questions. If you have any more questions, please post them. I'm happy to help.